This video presents a brief introduction and the main novelty of our paper, a generalized synthesis technique for high-order and wideband 3D frequency-selective structures with chip-check functions. 2D FSS has been widely investigated in many applications. It has easy fabrication and developed modeling and design methods during the decades of research. Unfortunately, it suffers from narrowband equivalence and acceptable performance. In recent years, 3D FSS has been proposed with its higher design freedom and superior performance. However, it usually has complicated topology and lacks the unified synthesis method accordingly. So, how to model the 3D FSS exactly and how to design the 3D FSS efficiently become the most crucial problems. In our previous work, we have found a kind of transmission line type structures which can be modeled exactly, such as stacked slotlines. Here is the element of the stacked slotlines. From the animate electric distribution, it's obvious that the incident spatial waves can be converted into guided waves and transmit through the slot line. Finally, they are converted back to the spatial waves on the other side. The entire structure can be exactly modeled by this equivalent circuit model. The interface is established by the model conversion network, and the slot line is represented by a transmission line. Now, we can realize the filtering response via the model conversion in the slot lines. In other words, the filtering structure can be achieved just as the planar circuits, inspired by the typical wideband planar filter as this. A wideband transmission line type 3D FSS is proposed as well as its equivalent circuit model, which is composed of slot lines and microstrip lines. According to the synthesis method of the wideband filters, the proposed 3D FSS can be also synthesized systematically. The 3D FSS prototype is assembled and measured in a mechanical chamber as shown here. Then, a wideband 3D FSS with 4 transmission ports can be obtained. Besides, by adjusting the bandwidth of microstrip line, 2 additional coupling paths can be flexibly introduced. Therefore, 2 transmission zeros appear at both sides of the passband. This improved prototype is also assembled and measured in the same way. Thank you for your attention.
In this video, a bandpass absorptive frequency-selective structure with wide absorption bands is introduced. It utilizes a combination of 2- and 3-dimensional elements. The research related to this design can be found in the IEEE Transactions on Antennas and Propagation. A conventional absorber absorbs electromagnetic waves at the fundamental frequency, f0, and the third-order mode frequency, 3f0, while reflecting the waves at 2f0. To achieve a wide absorption band, lossy layer 2 can be added to eliminate the reflection at 2f0. However, the presence of the lossy layer 1 weakens the absorbing ability of lossy layer 2. To address this, an open-ended transmission line can be inserted in lossy layer 1, operating in a half-wavelength mode. This modification allows for the realization of infinite impedance and ultimately leads to the achievement of a wide absorption band. Furthermore, a parallel LC resonator is inserted in lossy layer 2, and the metal reflecting plane is replaced by a bandpass FSS. This addition introduces a wideband transmission window within the wide absorption band. In this structure, the 3-dimensional lossy structure and the 2-dimensional lossy layer work together to broaden the absorption bands, while the 2-dimensional bandpass component enables a good passband. This hybrid structure offers wider absorption bands compared to conventional two-dimensional AFSSs and simplifies the realization of polarization-insensitive performance in comparison to previously reported three-dimensional AFSSs. A dual-polarized AFSS is achieved by combining a three-dimensional absorbing structure, an absorbing/transmitting layer, and a two-dimensional bandpass FSS. The equivalent circuit model of the absorbing/transmitting layer is modified, resulting in an accurate equivalent circuit model. The results from both full-wave simulation and circuit simulation agree well. A prototype of the dual-polarized bandpass AFSS is fabricated and assembled to validate its filtering and absorbing performance. According to the measured results, it achieves a transmission band with a minimum insertion loss of 0.88 dB and a 3 dB bandwidth of 15.1%, ranging from 6.44 to 7.49 GHz. The lower and upper absorption bands span from 1.53 to 6.15 GHz and 7.73 to 12.03 GHz, respectively, with respective fractional bandwidths of 120.3% and 43.5%. The results demonstrate that the prototype exhibits a stable frequency response to /TE and TM polarized incident electromagnetic waves.
This video will briefly introduce a transmission type cross-polarization converter that is featured by its polarization insensitivity. The relevant work can be found in IEEE transaction on antennas and propagation. Polarization diversity is widely used in imaging radar and wireless communication systems. Linear polarization diversity can be mechanically realized by rotating the transmitting antenna. It is very inconvenient to rotate a transmitting array antenna together with its complex feeding network. Another simple way to realize polarization diversity is to impose a polarization converter in front of the antenna's radiating aperture. However, most reported polarization converters are polarization sensitive, which requires that the converter structure must strictly align with the polarization plane of the incident wave. This work creates an FSS structure of chiral geometry to eliminate the polarization sensitivity. Following are some details. The FSS-based cross-polarization converter is designed through two steps. First, an FSS structure is built up with rotationally symmetric four-fold supercell in transverse direction, and it is a mirror structure in longitudinal direction. In this case, the rotationally symmetric four-fold structure can respond an incident wave polarized in arbitrary azimuth direction and make the incident linearly polarized wave pass through without polarization change. Second, by rotating each subcell patterns on the bottom layer by 90 degrees, the FSS structure becomes a chiral structure in longitudinal direction. In this case, the FSS structure makes the incident wave pass through and convert it into its cross-polarization state. The working principle can be explained as follows. A linear incident wave polarized at arbitrary azimuths can be resolved into two orthogonal components. The orthogonal components are independently responded by the orthogonal subcells of the FSS structure, and then the transmitted wave is combined by the two transmitted orthogonal wave components. Such a principle makes both the FSS and FSS-based cross-polarization converter are polarization insensitive. The novelties of this proposed cross-polarization converter lie in its high transmittance, high cross-polarization conversion efficiency, and polarization insensitivity for the incident linearly polarized wave. More details of the work can be found in the reference. Thank you for your attention.